Welcome to Lecture 10 of Quantum Complexity Theory at Paderborn University. This is the Winter 2020 offering. Today I have two quick announcements for you guys. Assignment 5 solutions are out. They're on Panda as usual. Assignment 6 has been released. It was released last week, and so it's due next week on January 26th. A6 will be the last assignment of the semester. Okay, so today we're doing a fun topic. It's BQP versus the polynomial hierarchy. This lecture is doubly fun for me because I get to start with my favorite quote, or one of my favorite quotes by Tolkien, in fact. I'm sure many of you are familiar from Lord of the Rings, so that's where this comes from. And the quote goes as follows. It says, "And it is also said," answered Frodo, "Go not to the elves for counsel, for they will answer both no and yes." "Is it indeed?" laughed Gildor. "Elves seldom give unguarded advice, for advice is a dangerous gift, even from the wise to the wise, and all courses may run ill." So here I'm really focusing on the idea that when you ask an elf for advice, right, the elf supposedly always answers both yes and no, right? And in a sense, oracle separations are exactly the same way. Okay, so let's get to this in a second. Let's first motivate the lecture by setting the context, right? Recall that in assignment 3, we proved the Sipser-Gax-Laudeman theorem, which stated that BPP is contained in the polynomial time hierarchy. Okay? And of course, if you see this statement, right, the first question you might ask as a result is, well, could the same thing be true for BQP? Question mark. Is this true? So this is the focus of this lecture, this question, right? And at first glance, you might think that this question has absolutely nothing to do with what we did last week, which was boson sampling, right? But in fact, in some sense at their core, they're really leveraging the exact same fact about quantum computations. And it's the following, right? To prove the containment BPP in pH, we really strongly leveraged the fact that a classical randomized algorithm can actually be viewed as a deterministic machine which takes in randomness as input, rather than being inherently randomized in some sense, right? You can decouple the randomness from the computation. And the same thing was true last week. We proved the no-go theorem against classical randomized computations, essentially, being able to solve boson sampling up to some non-standard conjectures, right? And that theorem crucially used the fact that, again, a BPP machine can have its randomness decoupled from its deterministic part, okay? And so if that was the key, underlying fact that was used in, this statement, well, we don't know how to do something similar for BQP, right? For all we can tell, the randomness in a quantum computation is somehow inherently there. We don't know how to decouple it, right? It seems to be part of nature. And so you might expect that, this containment should not hold, at least certainly not using similar techniques, right? And indeed, the general, I think, consensus or conjecture in the field is that BQP is not contained in pH, right? Okay. And of course, nobody knows how to prove this, right? In general, showing such strict containments or lack of containments can be quite difficult. So we tend to settle for the next best thing. What is the best thing we can prove? An oracle separation. Okay, so roughly speaking, the idea here is that we have a BQP machine versus a pH machine. They're kind of duking it out, if you will, right? And we give each of them access to some special power, the same special power, right? So some oracle A, let's say. And basically what one can show, and what we'll sketch today, is that there exists an oracle A such that, a BQP machine with access to this oracle A can do something that a pH machine with access to the same oracle cannot. Okay? Now, we started this quote about elves answering yes and no when you ask them for advice, and an oracle separation is kind of the same. So in general, an oracle separation doesn't really tell us whether or not a pair of complexity classes is the same or not, right? So we cannot conclude from this statement here that these two classes are different, right? Nor can we conclude that they're the same, right? So an infamous example right, that's well known in the literature is that, there exist oracles A and B such that with respect to one oracle, P and NP are the same, but with respect to the second oracle, right, P and NP are different. Okay, so in this sense, having an oracle separation is not conclusive proof separating the two classes, right? Nevertheless, of course, we really like oracle separations, well, primarily for the reason that, first of all, it's the best we can do in many cases, right? So it gives us some intuition as to if only I could endow, or at least what kind of powers should I focus on to separate two classes, right? In some sense, it gives you some flavor from that. And the second is that, if you want to prove, for example, that P is equal to NP, right? Well, we know that there's an oracle separation between the two, so any proof of equality would have to be so-called non-relativizing, right? It would have to break down when you start adding oracles to the picture, right? So it should really leverage the structure of the classes in question, right? So oracle separations are useful in those regards. They give you some sense as to the roadblocks to showing maybe equality or inequality, okay? Good. So what I'm going to do today in today's lecture, right, is we're going to lay it out as follows. There are going to be some nice tools that I think are worth seeing at least once during your theoretical CS careers, including the study of Fourier analysis for Boolean functions, right? And so in the lecture notes there is a link to lecture notes of Ryan O'Donnell, basically, which I strongly recommend you look at if you're interested to learn more about analysis of Boolean functions. In the meantime here, what I'm going to do is I'm going to start in section 1 of the notes by first stating the key claim regarding this oracle separation for BQP versus PH. Okay, so we'll state the claim, we'll analyze it, and then, well, okay, until I state the claim, I can't really tell you what's going to come next. So let me state the claim first, okay? Okay, so throughout, so let's start here. Let me be clear. So throughout, I really want to be clear that I'm going to define capital N as being 2 to the little n, right? And little n is my input size. Okay, so let me be really clear. Throughout this lecture, capital N is exponential in the input size. Okay, that's just for convenience. I don't want to write 2 to the little n over and over again. Okay, so here's the main theorem. I'm just going to write it down. Just get it off my chest, if you will. Okay, the theorem says the following. So let U2n, capital N again, so this is exponentially large, denote the uniform distribution over basically Boolean strings, although we're not going to work in the 0-1 basis. It'll be more convenient to work in the plus-minus basis, plus-minus-1 basis. Okay, so all strings of length 2 to the n essentially, but encoded in the plus-minus-1 basis. Then there exists a distribution, and it's going to be an explicit distribution. We're going to write it down. D. Okay. Again, it's over the same space. Right. We're going to be comparing these two distributions. 2n, such that two properties hold. Okay, so I'm comparing the uniform distribution over this funny other distribution D I haven't told you about. And the whole point is, remember, we're trying to separate BQP from pH. Okay, so the two properties will have to do with something being easy quantumly versus hard classically. So it's going to be that distinguishing these two distributions is easy quantumly, like whether I give you U or D. Okay, so in particular, there exists a quantum algorithm distinguishing, and maybe I'll erase this for now, the uniform distribution from this other funny distribution D. And there are two properties I care about. So with so-called advantage scaling like 1 over the log of n. Remember that this is going to be 1 over poly in the input size because n is exponential in the input size. And the other property it has is that it does so in time order log of capital N, which again, remember, is polynomial in the input size. And it only needs one input query. Okay, so quantumly, this is easy. It can be done in time polynomial in the input little n. Okay. So both in terms of gate complexity and query complexity, let's be clear. And of course, we want this to be hard classically. That's the whole point of this. Distinguishing is hard classically. Okay, so what do we want to say? We want to say that any now Boolean circuit of size quasi-polynomial in capital N and constant depth, this is important, we'll see why shortly, cannot distinguish d from u to n with advantage, quote unquote, better than order polylog capital N, meaning polynomial in the input size, okay, over essentially exponentially small, square root of 2 to the n. Okay, so this is the main claim, right? And now, of course, the rest of this section is going to digest this claim. So in particular, I strongly encourage you to pause this video right now, have a look at the theorem, try and digest it, what it's trying to say, right? And identify, a very important skill to pick up when you're trying to digest technical material is, can you identify what you understand and what you don't understand, right? What might need more clarification? What's not really fully rigorous or formal yet? Okay, so I want you to take a moment to do that. And when you unpause, we'll continue. Okay, so to digest this theorem, basically, the key idea here is that here you'll have advantage, whatever that is, right? Clearly, that's not formal yet. 1 over poly in the input size, little n, whereas here the best advantage you can hope for is going to be essentially exponentially small in little n. It'll scale like 1 over square root of capital N. Okay, and here, your circuit is polynomial in little n. And, the Boolean circuit here is quite large, right? It's quasi-polynomial in capital N, okay? Now, let's digest all the ingredients of this actual statement, okay? Because there are a few things that are clearly not clear, right? So, first of all, we should be clear about what we mean by Boolean circuit, okay? We should be clear, I already wrote this in quotes, right? What does advantage mean? These distributions, right? I told you that the input size is little n, and yet I'm telling you the distribution is, over this exponentially large space. So how are the machines accessing this, right? Certainly you cannot write down the full strings, okay? And something which may or may not be obvious to you is, let's just be clear. What do we mean by quasi-polynomial? How are we defining that? Okay, and there's one more big one, but I'll leave that to the end, okay? So first, well, okay, maybe I'll say that now because I'm going to address that in the second lecture. But the second thing, the last thing is that in this statement, right, we're separating polynomial time quantum computations basically from, quasi-polynomial and capital N Boolean circuits of constant depth, right? I made this in red, right? There's nothing in this statement that says anything about polynomials, the polynomial hierarchy, right? Alternating quantifiers, right? Like we're talking about constant depth circuits, so what gives, right? I thought we were having a lecture on, the polynomial time hierarchy, right? Not constant depth circuits. So we'll have to address that, and that will be in section 1.1. There's a whole section devoted to that because it's a nice connection, right? And it's a known connection. So first, let me clarify, though, these points in red. All right. So the first thing I want to clarify is, what is a Boolean circuit? Let's be formal about that. So clarifications. So number one, what is a Boolean circuit? All right. So we're going to have, it's of course a classical circuit, right? That much is clear. But you're allowed to have unbounded fan-in and OR gates. Okay, so that means that you can have an AND gate where the number of wires coming in can be unbounded, basically. So it doesn't have to be 2 wires, for example. And you also get NOT gates. You're allowed to put these in as well. Okay, we have a single output wire. Okay, so you're outputting a single bit. The size, let's see, the size of the circuit is equal to the number of gates. That's how we're going to measure the size of the circuit. And how about the depth of the circuit? It's what you expect. Basically, the length of the longest path in edges from any input wire to the output wire. Okay, so here, of course, we're thinking of this as a DAG, a directed acyclic graph, right? Where you imagine you have a bunch of input nodes, and then you evaluate some gates, and then everything kind of goes to this one output wire right here. Okay, so the depth is going to be, if you were to try and compress this thing as much as possible, how many steps you need to go from any input to the output in the worst case, the longest. Okay. Good. So that's what we mean by Boolean circuit. Okay, so the hardness is for Boolean circuits. Now we're talking about advantage, right? What is your advantage in distinguishing the distribution D, which I haven't defined yet, from the uniform distribution? So let me define advantage. Okay, so for this, suppose I have 2 distributions, D and D prime. B distributions over some finite set X. Okay, so then some algorithm. This can be a classical or a quantum algorithm. I don't really care which one. Algorithm A distinguishes D versus D prime with advantage epsilon if I look at what is the probability. So imagine now I draw samples from my finite set X with respect to D versus I draw them with respect to the uniform distribution. Or sorry, I'm doing D and D prime here in a more general setting, right? So I draw a random sample from one of the 2 distributions and I plug it through my algorithm A, and I ask what are the odds that A accepts that input if I draw from one distribution versus the other one. Okay, what is this difference in probability? And we say you have advantage in distinguishing if that probability is epsilon. Okay, so in particular, what this means is that, in the classical case, if you were to pick a random sample input from D versus the uniform distribution, then the algorithm, the odds that it accepts in one case or the other, it'll be those odds will be extremely close, right? They will scale like 1 over 2 to the little n, okay, roughly. Okay, and now the distributions are over, remember I said the distributions are over strings of length 2 capital N, so exponentially large in the input size, so obviously we cannot write these things down in any sense. And so how do we access the input? Or how do we, the distributions? How are U2 to the N and D accessed? Okay. So the answer is kind of a standard answer, right? Which is that we give the algorithms oracle access to the string x. And this is this is your random sample, right? So each random sample is a string from -1 to 1. So you essentially give me a random string. Equivalently, you'll just give me a random oracle. Okay, and how does the oracle work? For the classical algorithm, it's allowed to perform the mapping. You give me the index of the string x that you want, and I will give you the ith bit, right? Is it -1 or is it 1? Okay, at position I. And this is for unit cost. Okay, and for clarity, I is in essentially, you need log n bits to index the entire string, right? xi is the ith bit of x. Okay. Now, that's the classical access, and quantumly, of course, we do the same thing, except we can do things coherently, right? So we can do the access in superposition, as we've done very often. So quantumly, we get to coherently, meaning in superposition, map. Same idea. So you tell me the index you want in the standard basis, right? And now instead of, I could have done this, right? But instead of doing that, we'll assume that we're implicitly doing the phase kickback trick. So instead, what's going to happen is I'm going to inject the phase ±1, the actual bit, as a phase. Okay, so here I'm going to put xi like this, via phase kickback. Okay, so if you've, I don't remember, did we use phase kickback in this course? If we didn't, go revisit our introductory course, Introduction to Quantum Computing course lecture notes. Look at something like Deutsch's algorithm or the Deutsch algorithm. Their phase kickback, for example, is used prominently. Okay, so we're just going to inject this thing as a phase. Okay. Good. And so that's basically the access models for the classical algorithm versus the quantum algorithm. Okay, and finally, I think this is the last one. What did we mean by quasi-polynomial? So no circuit that size quasi-polynomial in n is able to solve this classically with any sort of reasonable advantage, let's say. So let's just define that. So what's quasi-polynomial? So if I say quasi-polynomial in n, right, I'm thinking of order 2 to the log n. So this would be polynomial in n, right? First, if I do this, right? Yeah, I'm assuming I'm working base 2, of course. That's just polynomial in n. Of course, the base doesn't actually matter, but let's just assume it's base 2. But now I'm going to put a constant exponent here. Okay? And so now that's no longer polynomial in n, it's quasi-polynomial in n. Okay. Okay, so those are all the parts we need to digest the statement. So let's just revisit it one more time. Right? There exists some distribution, D, right? So that quantumly, there's a quantum algorithm that can tell, with essentially 1 over poly in the input size probability in some sense, right? It can tell whether the oracle is encoding a random sample from the uniform distribution or a random sample from D, okay? And classically, any Boolean circuit of this giant size, quasi-polynomial in capital N, and constant depth, I still have to explain this part, is basically going to do really poorly at this task, right? It cannot distinguish. The probability that it's going to accept something from D versus U, basically, is going to scale something like the difference in probabilities will scale like 1 over the square root of 2 to the little n. Okay, so these things are exponentially close in the input size. So that's the main claim of this lecture. And so, even if you understand, let's say, absolutely nothing of the rest, like this is the basic premise. Okay, so you can take this home with you. And now, let's just explain this constant depth thing versus the polynomial time hierarchy. Okay, so this is section 1.1. constant depth, or bounded depth more generally, versus alternating quantifiers. Okay, slash pH. Okay, so this is something that's kind of standard in the literature. I mean, but I'm just going to review it explicitly here just to make it clear. So let's, of course, start by recalling the definition of pH. Right, so let's just recall that definition 3, the polynomial hierarchy pH, and in particular its kth level, sigma k, is defined as follows. So if I have a language L is in pH, or sorry, sigma k more accurately, if there exists a polytime Turing machine M, which takes input x, okay, so an n-bit input, k proofs, right, so not one proof, but y1 through yk, and each of these are just polynomially long strings, n to the c long binary strings. And let me be clear, it's very important here that both k and c are constant. Right, so if k is not constant, if k is allowed to scale like a polynomial, you actually get all of p space, you get something stronger. So it's important that it's constant. And what's the property we want? Well, x is in the language will imply that there exists some choice of the first proof, such that for all choices of the second proof, there exists a choice of the third proof, and so forth. And q is just a general placeholder, right? This is going to equal to there exists if I is odd, or it's for all if I is even. Okay, so it just depends how many times you alternate it. And such that M accepts the input x and the k proofs. Okay, and that's in the S case. And in the no case, if x is not in the language, then it doesn't matter which first proof you feed me, there's some counterexample on the second proof. So that doesn't matter which proof you feed me on the third one, and so forth. Qk bar is just the opposite, or the other quantifier. So if qk exists, then qk bar is for all, yk. And now M will reject this input. Okay, so this is the key property we want. Okay, so this is pH, and now we want to show basically a well-known connection between these alternating quantifiers here, and in particular their bounded depth, right? Because the number of alternations is constant, and with constant depth circuits. Okay. So let's again. Let's just set, so I'm just going to be a bit pedantic here and rewrite this again. So again, I'm assuming capital N is 2 to the little n. And again, this is the input, just like before. And consider now an arbitrary Boolean function f. And this goes from capital N bits to 1 bit. Okay, so it takes in exponentially many bits. And again, the point here is that this is too many bits to write down. I mean, so this function's huge, so we're going to have access to it via an oracle, right? Via oracle access. Okay. Okay, so I have some oracle OX, right? Oh, sorry, let's be very clear. Sorry, I want to be a little bit more precise. This is not entirely correct. So consider your Boolean function, and then for any input, sorry, we won't have oracle access. For input x, right, in the space, this is very, very large, right? Good, so we want to evaluate the function on x, but we're given oracle access to x. We can't write the full thing down. Given via oracle OX. Okay, so you give the oracle the index just like before, and it will tell you what the bit is at that input, at that index. Okay, so here's the main lemma. Of this section, which is, suppose there exists a sigma k p machine. Okay, so a machine at the kth level of the polynomial hierarchy, M, which it's given two things as input. Number one, it's given a unary string, 1 to the n. So it's given a string of ones, basically of length little n. Okay, and the second thing it's given is, well, basically the input 0, 1 to the capital N via the oracle OX, right? So oracle access to this exponentially long input. Suppose it can compute f of x. Okay, so suppose this was possible. Okay, using k levels of alternation. Then I want to argue that there will be a bounded depth circuit that does essentially the same thing, right? So if you can do it via alternation, then you can do it via bounded depth, right? So then there exists a Boolean circuit of depth k plus 1, size, order 2 to the log of c prime, capital N, for some c prime which is constant, which computes f of x, again given access to O. Okay, so obviously they both need access to the input, otherwise you cannot do the computation, right? Okay, so this is the main lemma of this section. This is the connection, right? This says that if I can do, if I can compute, right, computes f of x, if I can compute this function given oracle access to x, right, using k levels of alternation, right, in the polynomial hierarchy, then I can again compute the function without alternation, but with a Boolean circuit of essentially depth k, you know, we have to add 1, right? And the size of the circuit will be essentially quasi-polynomial in capital N. Okay, this is the connection between alternation and bounded depth. And so, you know, intuitively, I mean, you sort of see how this is going to connect now with our statement, right? Because this says that if you can do it via alternation, then you can do it via bounded depth. So the contrapositive would state that if I can't do it via bounded depth, then I cannot do it via alternation. Or I can't do it in pH. And well, that's exactly what, let me remind you, the main theorem said, right? It said that we cannot do something in bounded depth, and therefore that implies that we cannot do it via alternation, and hence via pH. Okay, that's the idea. So, how do we prove this? So I'm just going to sketch this. I mean, it's, again, standard. And so how do we prove it? Oh, so by the way, let me be clear that, of course, the input to the function here is x, right? And it's really kind of given implicitly via the oracle, right? This oracle, this 1 to the n, is given just to allow the machine runtime polynomial in little n, right? It kind of explicitly forces it to have that kind of runtime, okay? But the real input, of course, is embedded in the oracle x. This is just like some padding, okay? Good, so let's prove this. Proof of lemma 4. Let me be clear, because we're going to prove a few things, right? Proof of lemma 4. So M is this machine computing this. And so the first exercise, and I won't state this here, without loss of generality, you can prove that M makes only a single query to the oracle for x. So it only asks for a single bit of x. Okay, and this is exercise 5. And the way you do this, right, is, I'm not going to really go into depth here in the interest of time, but roughly the way you do this is you're going to add 2 levels of alternation, right? Meaning you get to add 1 more existential quantifier and 1 more for all quantifier to M, right? M already has some quantifiers built in over its proofs, right? And intuitively, the idea is, well, okay, let me not give it away. I mean, I'll leave that to exercise 5, basically, right? Okay, so we're going to assume in this discussion that without loss generality, this alternating machine makes a single query to X. Okay, and the high-level idea now to convert this to a bounded depth algorithm basically is going to view these alternations exist for all now with a single query at the bottom in terms of a tree-like structure, like an AND/OR tree, basically. Okay? So here's the construction. Let me show you how this goes. We're going to view the action of M via its computational branches. Right, so remember that we can think of proofs, or alternatively, you can also think about a non-deterministic machine, of course, which is kind of branching among proofs, right? Those are equivalent views. So we're going to think of it this way, right? So we're going to have kind of the top node of this thing, right, which is supposed to give out the answer, right? Remember, the machine M is going to output a single bit, so we're asking, does there exist a first proof such that for all second proofs, so does there exist a y1 such that for all y2, we get to the end such that M accepts, right? That's the question. Is this true or not, right? And of course, M has access to the oracle OX. And so keep in mind we're making 1 query to the oracle by this previous exercise, right? And so what that means is that essentially you can fix all the proofs, right? And condition on all the proofs, then M can decide what single query it's going to make to the oracle, right? And we'll talk about this more in a second. But let's imagine how this goes in terms of its computational branches, right? So here we want to, of course, output the final answer, right? Do we accept or reject? Does M accept or reject? And now I want to know, does there exist a y1 that leads to accept or reject, right? And so how do I do this? Well, I can imagine this in some sense. I can think of the first layer of this tree as corresponding to all the possible settings of y1, right? So y1 is, does there exist a y1 which is of size n to the c, or capital N, right? So you can imagine all the possible settings for y1, right? So maybe you have all zeros, and the very last setting is all ones, right? There are n of them, right? N bits. Okay? And as long as the machine, this is essentially like an OR now, right? As long as my machine accepts at least 1 of these y's, right? Then we're good, right? Because all I'm saying is there exists a y that causes me to accept at this point, right? So if I just look at this kind of cut, and I've fixed everything else, the question is there some choice of y, so that at this point, there's some OR and some post-processing, of course, which I'm omitting in this picture, that causes this machine to accept. Okay. And now, of course, we're going to recursively apply the same idea over and over again, right? So in the next level, right, I have a for all over y2, and so the next level is going to be for all y2, right? And these are also proofs of size n, and so each of these guys now branches. And again, we have all zeros all the way up to all ones, and same thing here, dot dot dot. Okay, and of course there are nodes in between. And now, of course, for what does it mean to say for all? Well, for all is like saying an AND, right? It's saying that for all the possible settings of y, right, this ultimate computation has to accept. And so this says that it has to be, you're taking an AND over all these branches, right? This is essentially like computing an AND here, right? So this gate up here is doing an AND essentially over the branches. Okay, so we do an AND over all the branches because it's a for all, and then here we do an OR over these branches because here I just want to say that there's at least one kind of node I can plug in here now. Okay, that causes the final computation to accept. Okay, and so we just kind of expand this out towards the bottom, right? Over and over again. And now we get to the leaves, right? So these are the leaves now. Dot, dot, dot. Okay. And now, once you're at the leaf, right, where we've kind of used up all our quantifiers, right? So all these quantifiers, these are now all accounted for higher up in the tree. And so now I can view it at this point, right? Like, so imagine I picked a branch, right? Imagine I picked a branch. Suppose I'm thinking about this branch right here, right? This is equivalent to me setting all the proofs to all zeros, right? Because the very leftmost branch at each point was just, the setting of all zeros. So imagine this is equivalent to me setting all the proofs y1 through yk. This is maybe the last one, right? I'm setting them all to all zeros, right? So if I think about this branch, right? In this branch over here, the machine M now, as all its proofs, it's got all zeros. And now conditioned on that, it decides which, it's a deterministic machine, right? If you fix the proofs, it knows now which oracle position it wants to query, right? And it's only going to query one by the previous exercise, one position. Okay. So in particular, it's going to evaluate some so given the branch, basically y1 through yk, right? M evaluates some polytime function. So it's some deterministic function, of course, of y1 through yk, right? And what does this do? It takes in the strings, right? Here they are. There are k strings, right? Each of length n, and it maps it to an index, right? In the oracle of this giant string x, the input. Okay, so to figure out which input, to obtain index, right? So this is just going to be the index I that it computes, okay? And then it queries the oracle at that index, okay? And so ultimately, now it has all its proofs y1 through yk. It has, xi, the ith position in the oracle, and then it can do some post-processing. So it queries xi, right? And then it does some post-processing to figure out whether it's going to accept or reject. Okay, given all the proofs y1 through yk, given the answer to the ith query xi. Okay. So post-processes returns now 0 or 1, right? And in particular, what we can do is we can assume, without loss of generality actually, that conditioned on the way we can kind of abstract this out, given all the proofs, either it's going to output xi or not of xi. Okay, so the final machine, of course, is just going to output, at this node, right? When it does this query, right? Sorry, maybe maybe this is not quite accurate to put the output up here, right? Because here we're basically setting the proofs. Yeah, sorry. The outputs should be down here, I believe, right? Because here we're doing an OR over the first layer of proofs and an AND over the second layer of proofs, and finally we fix all the proofs, and now we do the computation and come up with the answer, the output, right? So without loss generality, we can view it as, you fix the sequence, the branches, the sequence of proofs, and I query, I get xi, and then either I output xi or not of xi, okay? Ultimately, it's a single bit function, right? The output is a single bit, right? So there are really only 4 functions you could apply in terms of xi, right? You either output xi, its negation, the constant 0, or the constant 1. And in those last 2 cases, you just ignore xi, your query altogether, right? But of course, if you're going to output the constant, and this is the exercise 6, right? If you're just going to ignore the output of xi, if your output does not depend on xi, and you know that ahead of time because you're given the proofs y1 through yk, at this point you know exactly what you're going to do with your query bit once you get it. then you might as well not make the query, right? I mean, it's just silly. It doesn't depend on the function at all, this branch. Okay, so this is kind of how we're going to view the computation. Okay, so you fix the proofs, you query, based on your proofs, you pick your index, and then you either return the answer or the negation of the answer. It's going to be one bit or the other, basically. Okay, and I'm almost done here. The last thing we need is that I said you either return xi or not xi. So why did I say that? Well, because then here, depending on the branch here, you may or may not want to inject a NOT gate, right? So maybe I'll abuse my notation a little bit here and imagine that if you want, you can apply a NOT gate, and then here's your, whoops, here's your output on this branch, okay, essentially. Okay, and so whether or not you want to apply a NOT gate, that depends on the machine M, right? It conditioned on the proofs y1 through yk, it knows what function of the Oracle query xi it's going to compute ahead of time. And so based on that, you put a NOT gate here or not. Okay. Okay, so that's the basic construction, right? And I mean, just stare at this thing, right? I mean, this thing is just doing OR gates, right? It takes these inputs basically, right? And then it computes layer by layer. It applies a layer of OR gates and a layer of AND gates. And so, I mean, you can literally think of this as staring at a circuit, right? So I think this is why, by the way, I originally had written here that the output comes here, because, you know, if you view it as a circuit now, right, these are going to correspond to kind of bits from the oracle that you kind of plug into this thing, and then you'll have layers of AND and OR gates now, and the final OR will give you the final output bit, right? So I think perhaps it depends on what view you're taking of this thing. And the final exercise, therefore, is, well, first of all, the depth of this. What is the depth of this thing, right? Well, for each proof, we had one layer of AND or OR gates, right? And so the depth scales with the number of alternations, which was this constant k. And so, so technically speaking, the depth will be 1 plus this. Okay, so the key point here is that it's constant, okay, as claimed. And what about the size of this thing? Prove that T has size order. I mean, so you kind of know this, right? I mean, this is kind of standard, right? So it's 2 to the n to the c. And it's very important here that it's n to the power c here, right? All to the I, right? And if you plug this into your geometric formula, you know, what you'll get is the claimed size, right? So for some constant c prime, this is going to be the size of the circuit. Okay, so there's a circuit. I took the quantifiers. So the basic premise is this, right? Remember that if there is an alternating quantifier computation m, right, that computes this function, and it's got, you know, a constant k number of alternations, then we're going to get essentially a depth k circuit, k plus 1 technically, of this size, quasi-polynomial and capital N, computing the same function. And the way we did is that every time we had an alternation, we mapped it to an OR over or an AND over all the possible assignments to that proof, essentially, right? That's essentially what's going on here. Okay, that's it. And so just to recap, this is exactly what we needed, because remember this says that if you can do it with alternating quantifiers, you can do it with bounded depth. But the main theorem we're going to show now in the rest of this lecture is that you cannot distinguish these two distributions, d from u, in bounded depth. And therefore, you cannot do it with alternating with a bounded number of alternating quantifiers. Okay, so now I can write down the outline for the rest of the lecture. Right? Number 1, I have not told you what is this magical distribution D. Okay, this hard distribution classically. And then, of course, we want to show that distinguishing D from UN2 is easy quantumly, right? And this thing is hard classically. Okay? That's what we're going to do in the remainder of this lecture. All right, so let's start with the first of these things, the distribution D, okay? So we're going to define this thing in two steps. First, we're going to basically give a simple continuous distribution, and then we're going to map that or round it essentially to a distribution over a discrete space. Okay, so let me tell you what I mean by that exactly. Okay, so as before, capital N means 2 to the little n. Let's set basically a parameter epsilon to scale like 1 over 24. So this is the the exact value, but the precise value doesn't really matter. The key point is that this denominator scales like poly of little n. Right? That's the key point here. Okay. Okay. So what are the two steps to defining the distribution capital D? Okay. So like I said, first I'm going to define a distribution over a continuous space. Okay, step 1. And then I'm going to round this to a discrete distribution in the quote-unquote obvious way. Okay? So first we define a distribution G prime. Okay? And now this is going to be over Rn cross Rn. Okay, so as you can tell, the sample space now is a continuous space, right? It's not a discrete set. And so what are we going to do? So first I'm going to pick, so by the way, this is of course what, right? This thing is basically our 2n, right? So there are 2n numbers here, real numbers. And so what am I going to do? I'm going to sample the first n real numbers, okay? And then I'm going to use the first n real numbers to compute the second n real numbers. Okay, so number 1, sample, let me write this down, the first n numbers. Okay, so in other words, sample x1 dot 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 xn, right? So this is just the first part of this in the reals independently and according to a standard Gaussian. Okay? And so therefore I get, so far I have x equals to x1 up to xn, right, as my vector. This is an Rn, right? Intuitively, by the way, this is essentially how you would come up with, if you were to pick a Haar random unitary, right? Each of the columns or each of the entries would essentially be chosen in the exact same way, and then you would, run Gram-Schmidt to orthogonalize things. But that's kind of roughly the intuition. It's like picking a random vector according to the Haar distribution, okay, roughly. So that's why we do this kind of independent according to the normal distribution. That's how you get that Haar randomness. Okay, and now the whole idea is that the second half of this vector, right, so I still have these n coordinates. These ones I'm going to correlate with the first half, which I've already picked. So the sampling is only done for the first n coordinates. So now correlate the second n numbers. Okay, what am I going to do? Right? So set y, and what is this? This is just the second n coordinates, right? It's literally going to be what? Well, x itself, I mean, I've written it this way, but I could have written x as a column vector, so let's think of it as a column vector. So if it's an n-dimensional, for n being 2 to the little n, I can apply the Hadamard to this thing, right? Because Hadamard tensor little n acts on a space of 2 to the little n, which is capital N. Okay, so in other words, in some sense, this is the Fourier transform, over an appropriate field of x, basically. Okay. So this is the Hadamard, the usual Hadamard gate. Okay, so what is the final output? So output, essentially the concatenation of these two, plus some rescaling. Okay, so the final thing we output is this z vector. And this is just, first we rescale by square root of epsilon. Remember, epsilon was up here, okay? Scaled like 1 over poly little n. And then I just concatenate these two. So if you want, you can think of it like x and then y as a column vector in R2n. Okay, so that's the output. The first half is genuinely random. It's Haar random. The second half is correlated to the first one with respect to the operation H tensor n. Okay, and now, this rescaling, why did we rescale? Well, roughly speaking, this thing scales like, 1 over poly n, right? Roughly speaking. And so this is going to allow us to conclude that with WHP, with high probability, WHP, for all I, all the coordinates of z are between -1 and 1. They're bounded. Okay, so that's one of the nice things about this rescaling. This vector, in principle, of course, it's over this continuous space, but with very high probability, and all the weight is concentrated in this bounded interval -1 to 1. Okay, so henceforth, I'm going to just assume this is the case, right? Assume henceforth. Okay, so, if you want to do it rigorously, you'd have to write down a probability, but I'm claiming it's with high probability this is true, so let's just kind of assume it's true from that one. Okay. Now, the second step, remember, is that this is going to be a probability distribution over real numbers, right, over this continuous space. And I really want, my oracle is defined not in terms of real numbers, right? It's defined in terms of bit strings, right? Bits, basically, which we defined in the +-1 basis rather than 0-1 basis, right? So I don't. So I want to instead be picking random vectors over +-1. Like those would be the entries, +-1. So that's what I need to do now. I need to basically step 2, round G prime to the real distribution D that I care about over this discrete space, which is +-1 n cross +-1, oops, n. Okay. And so how am I going to do this? Well, the idea is, if you're familiar at all with approximation algorithms where, you take a real number between, say, 0 and 1, and you round it to the scalar 0 or 1, you're going to do the obvious thing here, right? Same trick as using approximation algorithm, which is, because we're assuming each coordinate is between -1 and 1, basically you round the real number zi to either 1 or -1 with a probability that's directly related to how close you are to 1 or -1. Okay? So, the formula is pretty simple. I'll just write down. So you want to snap to the Boolean hypercube now, or do the rounding. So independently, for all I, so for all the coordinates, which are real numbers, set. So remember zi originally were, we're taking them from this vector up here. And so now I'm going to set zi prime, okay? The discrete version of this to be what? Plus or -1, right? With probability 1. And let me be clear here, plus or minus. So if you're talking about +1 over here, then you should use a +1 over on the right. If you want a -1 on the left, you should use -1 on the right as well. That's how this works. Over 2. Okay, so that's the probability with which you snap to either 1 or -1. Okay, so in particular, for example, as a sanity check, if zi was already 1, then the odds that you snap to +1 is going to be 1 + 1 over 2, which is just 1 with certainty, right? So that's the basic premise. And that's it. Now you just output this thing. So this part's entirely as one might expect. So now I'm going to call this thing z prime to differentiate from before. The full vector, which is now exactly what we want. Right? We just take each coordinate and just snap it to 1 - 1 with a certain probability. So why in the world did we do this? Right? So this is basically, the reason why we did this is because, the oracle works in this discrete setting, right? I mean, the bits of our string are not real numbers, right? They're 0, 1, plus -1, right? So ultimately, I needed a distribution over a discrete space like this, right? But it turns out that analyzing this directly is a bit clunky, right? It's actually a lot easier to play with Gaussian distributions. Okay, it's a lot nicer, a lot more things are known in some sense. Okay, so throughout this discussion, this is the basic idea you should keep in mind, right? We're going to be analyzing kind of the continuous case because it's a bit nicer, and then we'll have some lemmas that show that, without loss of generality, once you understand the continuous case, the discrete case is almost the same, right? You don't lose much. And in particular, one thing that's really, really nice, which I will not prove, but it's, well, maybe we could just mention the proof because it's quite simple. Exercise 9. Right, so of course these distributions are not necessarily the same. Well, they're not the same because the output space is different, right? Nevertheless, you can prove that the expected value of zi prime, okay, so that's this one, the discrete variable, right, and then this is exactly equal to the continuous variable. This was the original continuous value. Right, so here was zi prime, by the way. There it is, right? Okay, so of course we're snapping things down, but I mean the point is that I chose my, how do you prove this? It's simple, right? The expectation is just the probability of something happening times its value, right? And I've chosen, +1 to be weighted with a probability and -1 with a probability, so that when you literally compute the expectation, you just get back zi, right? I mean, and here I'm using the fact that, of course, the two events are weighted 1 and -1, okay? Good, so the point is that on average, on expectation, the discrete distribution and the continuous one have the exact same expectations, okay? They're the same. Okay, good. So that's the distribution D, that's it. Okay, so let me just recap, right? Essentially what we did is we picked, well, maybe I should look at this range. Essentially we picked random Gaussian distributed numbers between -1 and 1, okay, so that your mean is basically around 0, okay? And most of your weight will be concentrated around 0 in some sense, right? And then we snapped these to plus and -1 using this kind of standard rounding trick, okay? And the discrete distribution and the continuous one have the same expectations on each of the variables, zi. Good. So now we need to show that it's easy to distinguish this funny distribution D from the genuinely uniformly random distribution. Okay, so that's section 3. Okay, so this is quantumly. Oops. Okay, so how are we going to do this? Well, I'm obviously going to give you an explicit algorithm that does this distinguishing. The algorithm is very simple. It's probably going to look quite, well, at first glance it looks quite similar. We have to be just slightly careful how we define this controlled operation that's going to show up. So here's the construction. So let me just remind you, what is our goal? Given oracle access to z prime, right? So remember that's this up here, that's this discrete thing we had up here, right? So the way this works, right, is that according to either u or d, we pick a string z prime, right? And then we embed that in the oracle, and then the oracle gets sent off to, the quantum algorithm, who's supposed to decide whether we use the uniform distribution or D to generate the oracle. Okay? So given oracle access to the string we sampled z, or z prime, -1, 1, 2n, decide if z prime drawn according to D or according to a U 2n. Okay, so without loss of generality, what we're going to do, just to make the notation a bit easier, we're going to imagine that, let OZ be the oracle for OZ prime. Okay, just to save on notation, I'm not going to carry around a prime everywhere. Because, well, in fact, well, okay, maybe I should put a prime here, but because I'm not really going to use this terminology in a second for z prime, sorry. What we're going to do is we're going to split this oracle up into two kind of sub-oracles, which we can do without loss of generality. Okay? So we're going to split into OX and OY. And what's the basic idea? I mean, each of these oracles is going to be responsible for either the first n digits, remember up here when we picked, intuitively, when we picked z, how did this work, right? In the continuous case, the first half was x, right? That was the random part. The second half y was not random in the sense that it was correlated. It was just a function of the first one, okay? And so that's why, x is going to correspond to the first half of our vector. Y will correspond now to the second half of our vector. So in particular, we're going to have the x part. So the oracle x, if you give me index I, and notice how now z has 2n entries, but now I is from 1 to n. And it's because I'm splitting things into two parts, each of which will go from 1 up to n. So this thing will output zi prime whenever I give it an index from 1 to n, because those 1 to n is the first, the x part of my vector anyway. And the y part is going to be the y oracle. So if you give it index I, then now it's going to start at z prime of n. Maybe I should put an I here. N plus I. Okay, so now it's looking at, it offsets by n to look at the second half of the vector. That's it, okay? And, exercise 10 in the notes asks you to show how given black box access only to, OZ prime, that you can still implement OX and OY. Okay, so I'll let you think about that. Okay, and why am I doing, why have I split it this way? Well, because I'm about to write down a circuit which is going to call an oracle, right? And the oracle is going to take in a control wire, and depending on the value of the wire, if it's 0 or 1, it's going to either look at the x part of the string or the y part. Okay, so that's why, for convenience, we've written it this way. Okay, so here's the circuit Vn, and this is on n plus 1 wires, as you'll see. That's why it's called Vn, to distinguish. Okay, so let me just draw the circuit. This is figure 1 in the notes. So here I have 0. So first, control wire. Okay, what is it going to do? Well, surprise, surprise, it's going to do a Hadamard, and then a controlled operation, and then a Hadamard. And then in this case, we'll do an X, and we will measure in the standard basis. Okay, so control wire. And now we have the other wires, 0, 0, 0, 0, like this. Again, surprise, surprise, we do a Hadamard. And now we're going to put in an oracle. And obviously, the oracle is going to be the thing that, encodes the input Z prime, except now I'm going to define it this way. I'll say O of subscript C. And I'll define this in a second. I suppose you don't really need these Hadamards coming out if we're not going to read it. Okay, so, but that's the circuit, okay? And let me just define what I mean by OC, this thing, right? So if C equals to 0, right, because, sorry, this is the control wire C, right? So if the first wire is 0, then OC applies basically OX, the first oracle. And if C equals to 1, then it applies OY, right? So depending on how you set this first wire up here, it looks at the first half of the vector or the second half of the vector, right? And ultimately, that's what we want to do, right? If this thing were to be uniform versus, how do we know this thing is not uniform? Well, the second half, remember, was essentially the Hadamard of the first half, right? So that's why we're looking at these two halves in this way. Okay. So that's the circuit, right? And now here's the claim. Of course, we have to prove correctness, right? And now, henceforth, Z prime was the full random string of +1s and -1s, right? And so since my oracle is split into an x part and a y part, let me also split z prime explicitly into its x part and its y part. So I can write this as, x prime, y prime. So, and this is what? Each of these are just, the first and the second set of n coordinates. Okay, that's all. So here's the main theorem for correctness. So suppose Vn, the circuit that we just drew, outputs 1 when it measures 1, okay? Because remember that, well, I suppose we could have written it in a different way, but fine. Let me just be consistent with my notes. And outputs -1 when it measures 0, okay, because we're assuming that it's going to measure 0, 1. Right, so in other words, this is just observable z, right? If you think about it, this is the observable we're measuring, right? 1 minus 1 being the eigenvalues. Okay. So what is the expectation now of this circuit, right? Then the expected output of Vn, right, on, if first, there are two cases, right? If I first pick it uniformly, the string in the oracle, then I get 0. Okay, so, the expectation is right at the middle of this interval, -1 to 1. It's bang at 0, okay? And otherwise, if z prime is distributed according to d, right, I want this to be bounded away from 0, right? And indeed, it's going to be epsilon. I'll put that in red. And so it's 0 versus epsilon. And how big is epsilon? How far is it from 0? Well, remember that, epsilon, I think we defined it here, right? Yeah, there it is. So it's 1 over poly little n. Okay? So certainly something you can distinguish with the quantum computer. Okay, so that's the main theorem, that if you run this quantum circuit, then indeed you can distinguish these two cases with 1 over poly probability, basically. Well, let's be a little bit careful. These are statements about expectation, right? Whereas when we first defined the main theorem of this lecture, we said that we're talking about the quantum circuit having a certain advantage in distinguishing two distributions. An advantage meant that the probability of outputting a certain value given a certain distribution, the probabilities differed sufficiently much when you sample according to one distribution versus the other, that the circuit can tell which distribution you're doing the sampling from, right? But here I'm not talking about probabilities, I'm talking about expectation, right? And normally you have to be very careful. You cannot, just because your expectation is a certain something, you cannot immediately conclude something about probabilities right away, right? In this particular case, though, we get it kind of for free, it turns out. So this is exercise 12, that we can immediately convert this to a high probability statement. We don't need to apply like a Chernoff bound or anything fancy here. Okay. Prove this gives the proper advantage statement in our claim, in our main claim of the lecture, right? Which was stated in terms of probabilities, not in terms of expectations. Okay, so let me just leave it at that. So the main theorem we want to show now in this section is that if I run the circuit and I measure at the end, if I get a 1 and I output 1, if I measure 0 and I put -1, then I'll get either expectation 0 or epsilon depending on which distribution I started with. And well, I wonder if it's kind of... Okay, well, let's just work through it. It's not difficult to see it. It might look a little bit nasty when you first look at it, but it's not so bad. So proof of theorem 11, the one we just wrote down. Okay, so there'll be 3 steps to this proof. Right, step 1. The first thing I need to tell you is, remember that the output of the circuit, right, is just a single bit, right? It's just 0 or 1. So if I tell you, but my statement is in terms of expectation, right? But if I tell you the probability of outputting 1, then immediately that tells you what the expectation is, right? Because you could compute the probability of outputting 0. There are only two outcomes. So that's why in the first step, I'm just going to talk about computing the probability that Vn outputs 1. Okay, rather than expectation, because that's sufficient to get the expectation. So again, I'm going to relegate some things off to exercises to make sure we stay within the time. But exercise 13 states that, show that Vn measures 1 in the control qubit with probability, this expression I'm about to write down. So again, brace yourself. It's going to look a little bit nasty at first glance, but it's not so bad. Square root 2 to the 3n, little n, sum over I comma j in the range 1 to n, minus 1 to the I dot j, xi prime, y j prime. Okay, so that's the first expression of it. And once you have this, you can break it down. Okay, so once you have this, then you can kind of massage it into this next expression, which is a half. Okay, and what I'm going to do here is I'm just going to use the fact that, 2 to the 3n, what is that? That's just n to the power 3, like capital N to the power 3, and there's a square root on top. So it's capital N to the power 3 over 2, right? So by moving things around, first of all, I could rewrite this in terms of 1 over capital N and get rid of this funny square root factor that's explicit. And the other thing I'm going to do, and this is all part of the exercise, but I'm just kind of explaining how this works, is that this inner product, what you're seeing here basically, this is essentially going to, I could equivalently write it in terms of doing a Hadamard, taking the Hadamard matrix, H tensor n, and looking up entry I comma j of that matrix, and then I multiply by the same terms as before. Okay, so what's changed here? Well, this has changed, right? There, and this has changed, right? But the other parts stay the same. Okay. And now I'm going to give this thing a name because this is what we're going to focus on. So this is nothing other than a half 1 plus, and the key term I'm going to introduce is this phi term, x prime, y prime. Oh, wait a second. I think I have a typo here. This should be y prime, yj prime. Okay. So basically, I'm defining this nasty looking thing over here, this thing here. This is just phi of x prime, y prime. Okay, and this is the quantity we're going to analyze throughout, because once you know phi, right, then it's easy to compute, 1 plus phi and then a half of that, right? Okay, so just some clarification as to what you're staring at here, right? This thing here, this exponent I dot j, what does that mean, right? I and j are both numbers, right, from 1 to n. So this is basically the inner product mod 2 of strings. Think of them not as integers now, think of them as binary strings, I and j. Okay, so this is the standard view when you talk about things like query complexity. So again, if you revisit these lecture notes of like the Deutsch-Jose algorithm from our intro to quantum course, you'll see this kind of notation. Good. And that's it, right? So, and this is just the ijth entry of the matrix H tensor n. Okay? So that's the claim of exercise 13. I'm not going to prove this explicitly in the interest of time. What we will observe here, though, is that what kind of function is this in the variables? Well, it has two n variables, right? x1 through xn prime. And over here, it's got y1 through yn prime, right? But you'll notice that the power on each of the variables is always 1, right? So this is basically, technically it's bilinear, but it's more generally multilinear. Okay, so if you fix all the variables except for 1, the function looks linear. So it's a multilinear function more generally. Okay, and we're going to use that property throughout. The fact that there are no high powers showing up is going to be important. Okay, so now in the second two steps of this correctness proof, we're just going to understand what this quantity looks like, basically, in the two cases of which distribution we're dealing with. Okay, so in the first case, what is the expected output of Vn for if I pick that string according to the genuine uniform distribution? Okay. Now, the lovely thing of doing this thing, right? Well, okay, let me not say that right now. Let me just first write down what I want to write down. So exercise 15 asks you to show, basically, prove that the expected value, for if I pick basically z prime, which is x prime, y prime, if I pick this uniformly at random, right? So if I pick x prime and y prime in particular uniformly at random, and then I look at, the function, the multilinear function that I defined up here, this one up here, right here. Right, so if I pick random strings and I plug them into the function phi, what does it look like? What is the expectation? It's just 0. Okay, and so this is a very good exercise. I encourage you to do this. It's actually quite easy, but it's just you have to use the fact about distributions, basic probability theory that should always be the first thing you try whenever you see expectations. Right, so feel free to pause the video for a sec. See if you can convince yourself of this fact. Okay, so what is phi prime? Well, phi prime is just this funny thing here, right? And so it's basically a scalar, a sum, right? These are also scalars. And here are the random variables, xi prime and yj prime, right? So if I take the expectation of this thing, right? By linearity, the expectation is just going to be the sum over all these things, right? These scalars can be pulled out by the linearity of expectation, right? This is the very magical property about the expectation operator, right? And then you just take the expectation of this thing, right? So all I really care about is what is the expected value of xi prime times xj prime, right? And if you think about this for a second, xi prime is some either 1 or -1 with equal probability, and yj prime is 1 or -1 with equal probability. So on average, their product will be 0. The expectation will be 0, right? Because the product will be 1 with probability half, and it will be -1 with probability half. Everything's completely random. And so that means that their expectation now will be 0. Okay? That's how you essentially prove exercise 5. Okay? And so the point is that by using this property, you can conclude exactly our first claim, which is that this allows us to conclude that if z prime, remember, which is x prime, y prime, if this was distributed according to the uniform distribution, if I picked each of the entries uniformly at random, Vn outputs 0 or 1 with probability a half. Okay, so in other words, if you really picked a uniformly random string, the circuit Vn is just going to act like it's flipping a coin. Okay, in other words, its expectation is going to be 0. The probability, so stare at this thing. What was this? Remember this up here? This was the probability that Vn measured 1, right? It was a half times 1 plus phi. And this exercise showed that if I pick x prime, y prime uniformly at random, this phi goes to 0. So the probability of outputting 1 is a half. Okay, and therefore the probability of outputting 0 is a half, and so the expectation is 0. Boom, done. Okay, so that one's quite easy. It can look a bit messy, but there's no real, well, there is magic happening. The linearity of expectation is absolutely magic, but it's simple magic, right? It's something you should always keep at the top of your mind. Okay, good. And now the last step is step 3, which is we need to understand what is the expected probability of the circuit outputting, well, just in general, what is the expected output if I don't use the uniform distribution, but this funny other one. So this was step 2 up here. So what happens if I sample according to D? Okay. And so the basic premise here was that at some point earlier, right, I claimed that, remember when we defined this distribution up here, right, we did it in 2 steps, right? We first, picked a distribution over this continuous space, right, and then we discretized. So we had this nice multivariate Gaussian, right, and then we, crammed it into this discrete box, if you will, right? And I really want to work with the discrete box, but the Gaussian is easier to analyze. That was the claim, right? And indeed, now we're going to see that in action, because what we're actually going to do is we're going to analyze the continuous distribution in this case. When instead of analyzing D, I'm going to analyze that G prime, the continuous version before we rounded, and then I'll plug in a nice lemma that says that, okay, without loss generality, the values I computed for G prime carry over to D as well, it turns out. Okay, so here's our claim that the expected value of x prime, well, actually, let me write it as I did up here. And so let me leave that blank for 1 second here, of phi of x prime, y prime, right? So remember, what's the key difference, right? The key thing we care about is this phi, right? Remember, the probability of outputting 1 is essentially completely determined by phi, regardless of which distribution I plug in. So I just need to understand phi, and in the uniform case, the expectation of phi went to 0, and now I want to argue that in the non-uniform case, the expectation of phi goes to epsilon, something bounded away from 0. And so normally, of course, I want to put a d here, but actually it's going to be easier for us to put this funny continuous distribution G prime. Okay? And so this is what I claim right now. So let's first see why this is true. And again, I'm going to abstract some things away to exercise. So first, let's prove via exercise, meaning you will prove. Prove that so if you sample Z prime according to the continuous distribution and any I comma j in the range 1 to n, the expected value, I don't know why I wrote that. I think I could erase this sentence. It's redundant. Oh, I suppose I just want to say, okay, I guess we can cut this out, right? And just say, prove for any ij, right? If I pick the 2 strings at random according to this G prime, again, I want to be clear that we're not talking about D right now. Then, and I look at the inner product, the product xi prime, yj prime. What is this? I want it to scale not like 0 now. Like if this was uniform, this was 0, right? The answer was 0. But now it's going to be essentially epsilon, but up to some other factors. -1 to the, remember, this is the inner product between strings I and j mod 2 over square root n. That's the claim. Okay, so if G prime is this multivariate Gaussian, then this is the expected inner product between these 2 real valued variables. Okay? Okay, so certainly you're bounded, well, this is quite a nasty bound, I suppose, 1 over square root n. But it's going to disappear in a second, right? That's just for 1 entry right now, because I'm only looking at 1 fixed ij, but of course now I'm going to end up summing over all the ij, so I'm going to lose this exponential factor, which is good. So of course the goal was I don't care about 1 ij, I really care about the expectation of the full function phi, right? And so so via exercise 16, what can we now conclude? And linearity of expectation again, there's the magic horse. This is a claim, right? Now we can prove this thing. The expected value of x prime, y prime, distributed according to G prime, of the function phi of x prime, y prime, is equal to what? Okay, so now you're just plugging in linearity, right? And now you're going to get 1 over n, the sum over I comma j in n minus 1 to the I dot j over root n e to the x prime, whoops. So same thing, g prime, right? And then now x prime I, y prime j, and maybe I should be clear here that right here I have I and j, right? Okay, and what was this? So this thing I know, right? So here's this thing, I just computed it right here. Okay, and you know, this other part is just coming from our previous definitions of you know, the acceptance probability of 1. Okay, so just plug that in, and what you'll find when you plug it in is you'll get, well, I already have you know, a copy of n and a copy of square root n, and now I'll get another copy of square root n from here, so I'll get 1 over n squared out front. Okay, then I'll get, the minus ones will nicely cancel out because I have the same term twice, and over epsilon, right? And this is nothing other than epsilon, right? So as promised, you know, this 1 over exponential term has now disappeared. So the total expectation is epsilon. Okay, so per coordinate we're off by a tiny bit, but when you add all the coordinates up, you get a sizable deviation. Good. So this says, again, that if I sample according to the multivariate Gaussian distribution instead of uniformly random, my expectation will be bounded away by an inverse polynomial by epsilon from 0. Okay? The only problem is that, you know, again, you know, ultimately my oracle can't play with this toy, right? It wants to play with the discrete toy. Okay, it's a discrete kind of kid, I guess, right? So for that, we need the following lemma. So to map to the discrete distribution D, we're going to use this lemma. Again, I'm going to state without proof. And so let me just state the lemma, and then we'll just briefly parse it or digest it. So for any multilinear function f that takes in, okay, in our case, it takes in 2n, right? So f you should think of as phi in our setting, if you like, right? So for us, this is phi. The expected value, if I draw z prime according to the distribution D, right, of, yeah, maybe I should just put phi to begin with, right, a phi of z prime. Well, okay, I think the reason why I wanted to do this is because it's not really, okay, I don't believe this lemma in any sense is specific to the structure of phi per se, right? It's for any multilinear function f, right? So that's really what I'm trying to emphasize here. So you can think of phi in your mind, but I'm going to write f because it is a more general statement that is worth keeping in mind, I think. So if you sample according to this kind of discrete distribution versus the Gaussian one, prime, sorry, and again f of z, sorry, this should not be prime, right? So let me be clear, this is z prime here, and so you get z prime, right? And of course on the right hand side we're drawing a different sample, so it's just from z. Okay? So that's the claim, right? So the claim is that, you know, if I'm picking samples from either the Gaussian version on the one hand side, g prime, or the discrete version on the left hand side, d, and then I'm going to compute an expectation, right? I already claimed earlier that the expectations will be the same, right? That was an earlier exercise. But not only that, but we get something even stronger. It turns out that even if I pick the samples and don't just return them, but I even post-process after the sampling. If I post-process by a function f that is multilinear, right? So it's not an arbitrary function, of course, but if it's multilinear, then that post-processing is weak enough so that it doesn't ruin the expectations. The expectations will still match. Okay, so ultimately what this is saying is that even post-processing, quote unquote, with multilinear f keeps the expectation the same. Okay, and that's exactly what we want because up here, you know, I showed you that the expectation was epsilon when I sampled according to g prime, and I took my sample and I plugged it into the multilinear function phi. and I said it was this, epsilon, and by lemma 17, now I know that I could put a d in here and I'll get the exact same epsilon out. Magic, right? Cool. Okay. So that gives us basically the main claim of this section, right? Which was, just to recap, my friend, where are you? There you are. Okay. That, here, sorry, went right over it. Right, that the expected value of the circuit Vn, the quantum circuit, will be 0 when you give me uniform samples, and bounded away from 0 by an inverse polynomial when you sample according to d. Good. So that's good. The circuit is certainly poly-size, right? You'll notice, where's my circuit? There it is, right? So, you know, the circuit is size polynomial in little n, right? As opposed to capital N, which is the dimension, right? And it only uses one query to the oracle, as claimed earlier. Okay, so it's an efficient circuit in the input size little n. And now we want to argue, kind of the harder part of this result is to argue that classically doing this is hard. Distinguishing d from u2n is hard classically. Okay. So how are we going to do this, right? And so here we're going to use some really nice tools that I think are worth seeing at least once, even if you don't work in like classical complexity theory, let's say, which is Fourier analysis over the Boolean hypercube. Okay, and in particular, what we're going to do is that we're going to say, imagine we had some circuit, right, that can do this distinguishing. I could rewrite the circuit in terms of, you know, ta-da, a multilinear polynomial, just like before, right? Just like we had in the quantum setting. And then we can analyze the acceptance probability of this polynomial in terms of its Fourier coefficients. And we can argue that by studying the Fourier coefficients, we can argue that, you know, the classical algorithm, if it's bounded depth, I think it's bounded depth, right? Yeah, that's right. Any bounded depth, that's right. We wanted pH, so therefore the circuit has to be a bounded depth. Any bounded depth circuit classically is not going to be very good at distinguishing these circuits. Okay, that's the very basic premise of this. Okay, so the first thing I need to do is I need to explicitly remind you how we express Boolean circuits as multilinear polynomials, okay? Because that's going to be, again, the name of the game. Okay, I'm going to take my supposed magic Boolean circuit for doing the distinguishing, and then I'm going to embed it into a multilinear polynomial, and then I'm going to study via Fourier analysis the properties of said polynomial. Okay. Boolean circuits. Okay, so let's C be an arbitrary circuit, a Boolean circuit, mapping. Let's imagine we're working again in the plus minus 1 basis. Sorry, this should be a squiggly bracket. Okay, so it takes in n bits and outputs 1 bit. And now, I'm going to write down a simple lemma that's, kind of standard, which is that I can always view the circuit as a function, okay, a multilinear function. Okay, so here's lemma 19, and I'm just going to sketch the construction. It's quite simple, but it's very cute. So let f plus minus 1 to the n. So in particular, this works for any Boolean function. I mean, I wrote circuit C because that's kind of what we have in mind, right? The circuit's going to be computing the function, but in principle, we can also think of C as just a black box function if we like. Okay? So this is just some arbitrary Boolean function. Okay, and the claim is that then f has, and this turns out to be a unique multilinear extension. So an extension means going to mean some function g, basically, which also acts on a bunch of other inputs other than just the hypercube, but reproduces the behavior of our original function f on the hypercube. Okay, so such that two properties, right? G of x equals to f of x if if you pick any x which is on the hypercube, so any of the bit strings essentially, and we can break up g of x, right? Because g of x now is like a proper, multilinear function, right? It's some continuous object. It's not acting just on the hypercube, right? I can always express it as a sum of terms, right? And it's going to be multilinear function, so it's going to be a sum over, things like expressions like this, right? Monomials, basically. So I can't have squares anywhere. So I'm going to be a little bit more formal in how this is specified, right? So you can think of a sum over all subsets of the variables, right? So I have n variables in total. Here's n up here, right? So I take all subsets of n variables, including the empty set. And what I do is I think about the monomial that's formed by that subset, right? So xi, right? So maybe example, if my subset was equal to 1 and 3, then this monomial would be x1 times x3, right? That's all this is saying. Okay. So it's a sum over these monomials, and of course you have to allow some coefficients, right? And those coefficients have a fancy name. They are called the Fourier coefficients. So it's the Fourier coefficient of g with respect to the set S. Okay. By the way, these are real numbers, yeah? Okay. So that's the claim. You give me an arbitrary function, a Boolean function, and I could always kind of embed it into, or extend it into this multilinear function, g, which doesn't take in bits, but it takes in just real numbers. And of course, if you feed this thing a number that's not a bit, right, or a sequence of bits, it can do something totally different. But the point is that whenever I feed in a string, g reproduces f properly. Okay. And what we're going to do is we're going to take our circuit and embed it in such a g. And what we're going to see is that these coefficients, the Fourier coefficients, if I were to write it out in this basis, basically, by studying these coefficients, these weights, I can tell how well the classical circuit can be at distinguishing D from the uniform distribution. That's going to be the idea. But first, let's just remind you how this embedding trick works. So this is like standard, but for completeness, let's just sketch the proof, because it's good to see it at least once. Okay, so what we're going to do is the following, right? So again, I'm sketching, so write G as a sum, of 2 to the n terms, right? And where's this number 2 to the n coming from? Well, check it out. Like f takes in, there are 2 to the n possible inputs, right? It takes in n bits. And so what I'm going to do is I'm just going to explicitly work out for each possible input to f, I'm going to write the value down, and then I'm going to kind of hit that with an indicator function to make my function g basically disappear on all functions except the input, on all inputs except the input you want. So the best way to do this, I think, is via just one example. Okay, so I'm not going to do it explicitly. I mean, I will do it explicitly for one input, but I won't do it kind of in general. Okay, so let's just do let n equals to 3, and suppose you have some input x, right? And so what I want to do is I want to add to g a term that whenever you feed g the input 1 minus 1, 1, it will output the term f of x. I want to kind of brute force design g this way. So what do I do? Well, I put down f of x because that's the answer I want to come out whenever you feed this thing x. And now I just want to check, if you will, that each of the bits is right, that it's 1 minus 1 and 1. So this is my indicator function. So how do I make sure that if you give me 0 instead of, if you give me minus 1 instead of 1, this thing will disappear? Well, I do this, right? If I say 1 plus x1 over 2, right, as a product, right, if x1 is indeed 1, if it matches, then this thing goes to 2 over 2, which is 1. And so, this term will stick around. And if instead you were to give me minus 1 instead of 1, then this term goes to 0, and the entire thing is eliminated. Okay, so this is why I said it's an indicator function. And so now you could probably guess how to fill out the rest. I encourage you to stop the video and see if you could fill out there are 2 more terms here, right? What these will look like. I don't know why I did them in red. They are 1 minus x2 over 2, 1 plus x3 over 2. Okay? So this is just, for one this is just one entry of your truth table. Let's just suppose you have a 3-bit input. Maybe when the input is 1 minus 1, 1, there's some output fx, and this is how you write it as a multilinear function. So you'll notice that this is linear in x1, x2, x3, right? Because this is a constant, right? F of x, you've already plugged in x, so there's no variable there anymore. It's just you've looked up the entry in the truth table. So the variables are sitting right here. Okay? And this is your indicator function. Okay, so, and the basic idea is just this, right? That repeat this for each entry in the truth table for f, right? So this particular entry we looked at was 1 minus 1, 1, but there are 7 other settings. And then add all multilinear terms you get to obtain G. Okay, that's it. So just do it row by row in your truth table for f. That's the basic premise. Okay. Good. So this is, let me just review the claim. The claim was that, right, you have some circuit or some Boolean function. I can equivalently think in terms of a multilinear function G, which captures f on all the points on the Boolean hypercube, right? So that was this property right here. G of x equals fx if x comes from the hypercube. Good. Okay, so now we can talk about the tools and proof approach we're going to use to analyze this classical circuit. So henceforth, whenever I say C, you should think of this as being either the circuit we have in mind, or its multilinear extension. Okay, I'll kind of use this, I'll abuse this notation and I'll use back in, I'll mean both depending on context, okay? Okay, so just keep that in mind. Okay, so here's the goal. If C, right, and remember just to jog your memory, right, this is just a circuit that maps 2n bits to a single bit, is, well, remember we're restricted to constant depth circuits, and has size 2 to the log, I guess I wrote just C, some constant, C to n, then C cannot distinguish D from U to n, right? So this was the main goal. Constant depth circuits of quasi-polynomial and capital N size cannot distinguish these two distributions. That's what we want to show. And so, i.e., let me be slightly more formal about this. If I take my circuit C, right, now I'm going to use the multilinear formulation, right, and I plug in Z prime, which is distributed according to the expectation of Z prime distributed according to D, right? Actually, no, I don't think you need the multilinear part yet, right? Versus the expectation if I pick a U, I'm going to use U just to be clear, we're talking about the uniform distribution now. So U from uniform, okay, of C of U. So what's the expectation, the difference in expectation? Remember, we want to argue that this algorithm has not a good advantage, only bad advantage, right? So in particular, we want the difference in expectation to be very, very small. So the numerator is not so important. The denominator is the key point, right? So essentially, it's 1 over exponential in little n. Okay, and just to really drive you crazy and drive this point home, remember this is what capital N is. All right. Good. And so what are we going to do? To prove this statement, right, I'm going to look at its decomposition in terms of its Fourier coefficients, right, the multilinear extension. So, I mean, this is a lot like, I always like to think of this as somehow analogous to, it's not entirely accurate what I'm about to say at all, but, we've talked about things like spectral decompositions, right, in this course. We like to do that a lot for quantum, like if you want to understand the spectral properties of an operator, then this is exactly what you do. You take a spectral decomposition, and for Boolean functions, it turns out to be useful to look at its Fourier coefficients as well. So it's some sort of extremely rough analog of a spectral decomposition. Okay, think of it that way. Okay, so basic proof approach. So how are we going to prove that the classical circuit is no good at distinguishing? So this is exercise 23. And the first thing you want to do is you want to prove, and let me just remind you, this is going to be important. I'll just write it down again because I do want you to remember, like imprint this formula in your brain so that you'll see it when you go to bed at night. And also when you wake up in the morning. G of x, remember, was equal to sum over s subset of n, right, of the Fourier coefficients, g hat, I believe. There it is, yeah, good. Times pi of, I think I used I and s, xi. Okay, so this is the Fourier expansion again. Okay, so what I want to, and of course now we're going to be talking a lot about these Fourier coefficients, so that's why I'm putting this in your face again. So the first observation is you can prove that the expected value of, if we're first talking, usually the uniform case will be the easy one to analyze, right? Because it's just, well, it's completely random, right? So if I pick a little u uniformly at random of the circuit, right? And I instead think of the circuit as, in terms of its multilinear extension. Remember, C for me, it can be either the multilinear function or the circuit. So now let's think of C as a multilinear function. And remember that C and G will be different functions in general, right? The G is acting on a different space entirely, right? But if I feed in, points from the hypercube like this, I know that the answer of G and C will be the exact same. And so if you feed in a uniformly random bit here, right, what is the expectation? Well, the claim is that this will be not 0, but G hat of the empty set. Okay, sorry. Let me be consistent with my notes. Technically speaking, I might want to, okay, anyway, it's lagging again. There it goes, yeah, okay. All right, this will be, I'm going to be consistent with my notes, and just instead of talking about the Fourier coefficients of G, let me talk about the Fourier coefficients of C, right? Because I'm thinking about the multilinear extension. So maybe I should have written C of x here and C hat of x, okay? Same thing. So C hat of empty set. Okay, so remember that, we had a Fourier coefficient for each subset of n. So there are 2 to the n coefficients. And now there's the empty set coefficient. And why is this true? Well, just stare at this for a second. If I take the expectation of this expression, right, and I do it over, uniformly random points on the hypercube, plus minus 1 entries, right? Remember, expectation is linear, magic formula, right? So you're just looking at the expectation of this monomial, right? And if these guys are picked uniformly at random from plus minus 1, then their product on average is going to be 0, right? The expectation of the product. And so as long as you have, as long as the monomial is non-trivial, there's something in it, at least one variable, this expectation is going to 0. The only way this term is not going to get eliminated is if the subset S is empty, because then there is no monomial, right? It's just the constant 1. And when the subset is empty, you get precisely the Fourier coefficient, which is just C hat of the empty set. So the uniform distribution is really nice. Basically, it kind of just kills off all the higher order Fourier coefficients, and it just keeps, the 0th order one in some sense. Okay. Okay, and one thing I do want to remark here is that this thing is a constant. right? So C hat of the empty set is defined based on our circuit C, right? It has nothing to do with which distribution you plug into the circuit now. It's defined before you even pick your distribution, right? So, so this is some constant, okay? And so what is our goal, therefore? This is the starting point. The goal is to show that this is the expectation C hat of empty set when I randomly sample uniformly, versus now if I instead sample according to D, right? So this is sample with respect to U2n. That's the expectation. And now I want to argue that this thing, when I sample according to D of the circuit of C of Z prime, I want to argue that those things, that difference is small, quote unquote. Those two expectations are small. And so in particular, what we really want to say here is that remember that this term is a constant. It's independent of the distribution. So whether I plug in C or D, that term's always going to play a role. And so if I look at this term on the right, which again is the multilinear, same multilinear function, except now I'm plugging in a different set of inputs, right? Except now the inputs, the distribution I choose can have an impact on the higher order terms beyond the empty set term, because then the monomials are non-empty. And so whether I drew the x from D or U, that will have an impact on what the values are for the higher order products of a Fourier coefficient times some non-empty monomial. And so what we want to argue is that for these two to be close, the constant term is common to both, so those will cancel out, of course. And so all you really want to show is that the higher order terms in this expression, like all the terms in the sum, when I sample according to D, other than the base term, right, the constant term, all those terms should have small norm, right? Okay, they should have a very small value. That's the goal. Okay, so i.e. higher order Fourier coefficients have small norm. That's the goal. Okay, and by norm I mean infinity. One norm, basically, some of the absolute value. Okay. Good. So how do we do this? We're going to use a pair of tools. Right. This is basically what we want to show. We want to. This is our goal, and so here are our tools at a high level. Number one, we'll need tail bounds on Fourier coefficients, and we're just going to use this as a black box lemma. So here's a very nice lemma which says the following. Lemma 24. Let's see. Be a circuit, as in our case, of depth D, size S, and always remember that D for us is a constant, right? Then for any constant, well, okay, technically it's any natural number, but think of K as a constant. There exists another constant C such that the sum over all subsets of size 2 to the n such that the size of the set equals to K, right? So here's K, here's K. So you can fix your K, and presumably we want K to be strictly bigger than 0 here, so that we're not touching the constant term set, although maybe the upper bound holds anyway. And so we have the absolute value, and all I'm going to do now is just adding up the Fourier coefficients, right? All I'm doing is I'm adding all the Fourier coefficients of weight K, okay, where the size of the subset is exactly K. And I want to bound the kind of that level, if you will, right? And the norm, the one norm on that level is going to be at most, well, C is a constant, log S was one of my parameters, that was the size, right? And now I get D was my depth, and here's my K term. Okay, so what this is saying is that if my circuit is short depth, meaning constant depth. D is constant. And I'm thinking of k as a constant, right? Well, okay, k is supposed to be for any natural number. We'll see why in a second, but for now you can think of it as a constant. The point is that, this thing is bounded to be something quite small, right? It's like log of the size of your circuit to the power d to some constant, right? So it's some polynomial in log s, right? And so that's good, right? Because remember, our goal was to argue that all the Fourier coefficients here, other than the constant term, which again is going to be common to both terms here and hence cancel, as long as k is small, constant in size, then this bound is quite good, right? Because then the exponent is just a constant. Okay, so this is good bound when k is small. That's the intuition, right? And of course, that's what we want, right? We want to show that, ultimately I want to show that the sum of all terms other than the constant term, that's bounded. That's really what I'm going for here. But this will only work now for the terms of small weight when k is small. So how do you deal with the fact how to deal with large k, right? What about the higher weight terms? This lemma as a black box just won't cut it. And so that's why we need the second term, which is random walks. Okay. And the basic premise is this. We can simulate drawing samples according to D, right? So rather than kind of picking it in one shot, right, I can instead take a random walk with baby steps. Okay, and I'll explain what this means in a second. Okay, that's the basic idea. And the intuition now is that, when you take these little baby steps, right, then it'll turn out to suffice to use kind of just low choices of k. Then you can apply, this bound to each of the baby steps, k, and then kind of plug everything together with a big triangle inequality and, bound the weights for all k. That's roughly the idea. Okay, and we're going to be a little bit more formal now, of course. So apply, what name did I give this thing? Lemma 24 to each baby step. And then plus a big triangle inequality. Okay, that's the very high level view of how we're going to do things. Okay, so just to recap, we already know that for low order Fourier coefficients, we have a nice bound, right, when k is small. And now for when k is large, I need to have some one norm type bound like this on the sums of these Fourier coefficients. And I'm going to do this via this cute random walk simulation trick. And so that brings us to the last section, which is 4.3. Main theorem, and again, a proof sketch. Okay, and essentially, what this main theorem I'm about to write down, right? This is the kind of the main difficulty in showing the overall result of the oracle separation is, where did it go? This thing, right? So what was small over here? Well, now let me quantify what I mean by small. Okay, now let's write this out. So I'm going to show that if you sample according to D, right, then the expectation is essentially the constant term in the Fourier coefficient, meaning that the higher order terms are contributing very little. Okay. Okay, so here's the main theorem then. Let me write that down. So D, this distribution D, fools bounded depth circuits. Okay. So let's see plus minus 1 to the 2n be a circuit, Boolean circuit, classical, of depth D, size S, right? then, actually I don't want to underline that. I'll just leave it. The expectation, right? So this is the same statement as before. If I draw Z prime, right, my random sample according to D now, and I plug it into my circuit, or my multilinear polynomial equivalently, right, the expectation is going to be very close to just a constant term in my Fourier expansion. Sorry, there should be a absolute value bar. So this is the exact expression, 12 epsilon, right, epsilon being 1 over poly little n, don't forget, C log S, right, to, and maybe I should write these in red, D minus 1. Okay. And here's my epsilon as well, right? We picked this earlier, and then in the bottom I have square root n. Okay. So in particular, you know, D is a constant term, right? We have a log S here, so even if S is, you know, scaling like n, the log of that's going to be quite small, right? And so the key point here is that it's essentially 1 over exponential in n, right? 1 over square root of 2 to the power little n. Okay, so that's very, very good, right? I mean, in the sense that the classical circuit cannot distinguish. Okay, so this is what we want to prove. And to prove this, there's going to be one main lemma we're going to use. The main lemma is really just an application of, you know, I'm not going to show the proof of it, but here I said we're going to use 2 tools, right, to show our main result here. Number 1, tail bounds on Fourier coefficients, and this worked for the low order Fourier coefficients. And then number 2, these random walks down here, right? And now this lemma 24, which were these tail bounds, I'm not actually going to use them explicitly. Rather, they're used to prove this lemma I'm about to write down now. Okay, so that's why if you look in the lecture notes, you'll never actually see lemma 24 used, but it's worth seeing because it's very nice, you know, to know as a fact to have in your toolkit, right? But this is ultimately what lemma 24 buys us, and this lemma I'm about to write down is what we'll actually end up applying. So using lemma 24, one can show the following. Lemma 26. Fix any p, which is at most a quarter. Okay. C is again a circuit. Its depth D, just like before. Size S. Somehow the colors didn't work out just right. And such that the square root of epsilon, which epsilon is our parameter from before, here's p. Oops. That was not very good. Good. Just leave it like that. Square root epsilon p times c log s to the d minus 1. So this is this expression we see up here. Okay, very similar to it, except, you know, there's this additional factor of p in here, which is at most a quarter. Otherwise, it's this thing over here. Right, there you go, right here. So the point is that, you know, this could be large, right? But the point is that I'm taking this thing and I'm pre-processing it with this p so that I can bring its value down, so it's going to be at most a quarter. That's all this is doing, right? So I'm hitting it with a small enough piece that that value is bounded. Then, for any z naught in the range -1/2 to 1/2, the expected value, and again we'll parse this in a second, the expected value of z drawn according to g prime of c C0 plus PZ. Let me put P, you know what, let me give P a color because we're using it quite often here. Okay, there it is. Sorry, PZ minus C of Z0. This thing is bounded. Okay, so again, this looks quite cryptic, so we'll parse it in a second. So this thing is what? Well, 12 p squared c log s 2 d minus 1 all over square root n. Okay, so what's happened here is that, I wanted to prove this bound on the right here, right? So what I did is I took, this part over here, and I scaled it down by this term p over here, so that the scaled down version is at most a quarter. And then when I do that, I get some funny quantity on the left. It's going to be upper bounded by something very similar to what I wanted up here, right? But not quite. You see the difference is I still have a p now. That's new. But up here I only introduced one copy of p, but here I have p squared. Okay? So you're getting this kind of extra damping factor of an extra copy of p being hit on the right-hand side. Okay, so now let me, so just observe that for the right-hand side. What is the left-hand side intuitively saying? How are we going to use this? The idea is that, imagine I'm doing a random walk now, right? So remember, in a random walk, what you do is maybe you pick some assignment, let's say z0, and maybe that's just, or in our case, maybe it's plus minus ones instead of zeros and ones. And then, you think of all the neighboring terms on the hypercube, like maybe 1, 1, 1, 0, 1, for example, right? And then, you pick one of your neighbors uniformly at random and you go to that one instead, right? To the next string. And so that's the type of thing we're doing in a random walk, right? And so suppose right now in the random walk, what is this lemma saying? Suppose I'm currently at z0 in my random walk, okay? And so, c of z0, I can plug it into my formula that has some value. And now what I do is, imagine here's my current point, and I perturb myself just a touch. Okay, and so here I'm really using the fact that I'm taking baby steps. And also the fact that, of course, c is not a Boolean function now. I'm thinking of it as a multilinear function, right? So I can certainly apply it to something that's slightly perturbed away from z0. Okay, so pick z according to g prime, right? Remember, we're assuming that the coordinates of z are all between 1 and minus 1. But on top of that, I hit you with this small factor p, right, to scale this thing even further down. So these are really like little baby steps away from z0. And the claim is that, how much does the function c change when I move from my current point z0, right, to, some random point according to, pick something from g prime and kind of scale it down so it looks like a baby step. And then I go to this random small perturbation, and I check my c there. How much do those two things differ on average? And the answer is not much, right? You have this giant exponential scaling in the bottom, and you have this extra suppression by an additional factor of p in the numerator. Okay, p is, remember, some small number here. Right, so the basic premise here is that, therefore, to simulate drawing z prime according to d, right, which is what I really want, we instead are going to run a random walk with baby steps of small order. Okay, so that basically means that I'm going to choose this p, this damping factor, right? It's going to be very, very small, 1 over square root n. Okay, that's the basic idea. Okay, so again, we're going to use this right now in the last sequence of equations below to argue that every time I take a step in my random walk, right, my value of c is not going to change too much on average. Okay. Okay. So let's do a proof sketch of Theorem 25. Okay, and let me just remind you what the theorem said again. Right here. It said that if I have a circuit of depth d, size s, then the expectation if I draw samples according to d and I cram it into my circuit C, that expectation is going to be very, very close to the constant term in the Fourier expansion, right? So all the higher order terms in this function c, right, are basically really, really small. Okay, and how small? Well, it basically scales like 1 over the square root of capital N. That's what we wanted to show. And so instead of sampling according to D now, I'm going to use this random walk with little baby steps to simulate this sampling process, right? That's the basic idea. Okay. So as a starting point, assume, without loss of generality, that the square root of epsilon c log s d minus 1 is bounded by a quarter n to the quarter, because otherwise basically the claim will be vacuous. So let's just assume this. And now here's the random walk. Run the following random walk for t equals to n steps, right? And the perturbation size is p equals to 1 over square root n, right? That's what we set up here. Okay, so we're taking really baby steps. So what is this random walk? Sorry, let me not do that. So rather than drawing a sample directly from D, right? What I will do is I'll draw T samples. Remember, T is up here, right? It's N, capital N, so these are a lot of samples. So draw a bunch of samples. Z1 up to ZT, right? And these are all distributed according to G prime, okay, as our proxy for D, remember? And now what's going to be the output of the ith step, right? I mean, you can think of it as drawing these samples all at the beginning, or if you want, you could sample them one at a time. It doesn't really matter. But the point is that to make it look like a walk now, right? Set the output of quote unquote step I of the random walk. And here I is just in the range 0 up to t, right? Because I've taken t samples in this line. Here's a little t, right? So I only have t samples in hand. So what do I set it as? So that's this thing. It's going to be z less than or equal to I, right? So the output of the ith step of the walk is going to be this thing. It's going to be add up all the terms, right? Each of these is a vector, right? I've sampled z1 up to zi. So first you add up all these vectors distributed according to G prime. Okay? And then I'm just going to rescale it all. I'm going to rescale it by this p term. Okay? So it's like, instead of taking one sample, right, I take a bunch of them, I add them together, and I rescale them down. Right? And the point here is, of course, that each of these terms is kind of, well, very small, because p is very small, right? Okay, and in fact, a lot of these are, well, each of these should also be very small, right? The entries are all between, well, I guess the one norm can still be big. Okay, but p is very small, right? And what's the key point here? I won't show it here, but one can show that if I look at this full thing, right? So I defined it up here for, I defined this up here for I, right? But if I plug in t, if I really run it all the way through the end, right? I took t samples. So if I add up all the samples now, and then I renormalize by p, if you will, this thing is distributed according to G prime itself. Okay? In other words, the random walk reproduces G in this sense. Okay. Now, why in the world are we doing this? Well, because it's we're gonna break the sample. This is just some way to break the sampling of G prime into small baby steps so that we can analyze each of the baby steps one by one rather than them as one big joint action, right? And so what do we do? Now for any step I, each entry of, the ith step of the walk, right? So this is, remember, I just add up the first I vectors and I hit them with P, is Gaussian. And its variance is going to scale roughly like, P squared epsilon. I'm not going to prove this, right? But you could probably just look it up. But this means that, the variance is quite small, right? Because P is very small, so I'm hitting it with P squared, basically. And so that means that if you're a normal Gaussian and your variance is quite small, well, guess what? You're going to be very close to 0 on each coordinate, right? And that's precisely what the claim is with high probability. If I look at any of these guys, right, they're always going to be in the range minus, not 1, but minus a half. It's going to be quite close to 0 in this sense, right? So you have 2 n coordinates, right, in total, and each of the coordinates is kind of concentrated around 0, okay? And why do we want this? Well, this was as required for lemma 26. Okay, so remember the whole idea is that I want to be able to use lemma 26. Let's see if it's going to let me scroll. We are nearing the end of the lecture, and so it's going to lag a bit. Where's lemma 26? Should be just... There it is, I think. There it is, right? So remember that... right. So remember that this says that, if my points are in this range, right? Then, oh, did I want to put... Might be a typo in the notes. I suspect there should be an n here, right? Because it's not just a single value, it's a vector, right? Okay, so as long as your point is sufficiently mixed in some sense, it's sufficiently close to 0 as opposed to like the true values on your hypercube, then these moves, these baby steps are not going to change your expectation much, right? And so now I've satisfied this precondition, right? My points are going to be in this range, and now I can apply lemma 26 to argue that the difference in going from my current point to my current point plus some small perturbation, that's going to be very small. Okay, so let's do that. So this implies what? It implies that the expected value of, well, first let me start with the expected value of C on my current step, right? So right now I'm at step I, right? And so I have some expectation for that, right? And now I want to know, how does that expectation change as I go to the next step, which remember is a baby step by definition. We were hit with this giant factor of P, well, inverse giant factor. And now I want to go to Z I plus 1, right? And here it's just I. So how much does the expectation change of the circuit, right? And let me just remind you, this is the circuit. This thing, when you plug it into just by lemma 26, right? This is just by lemma 26. 12 epsilon p squared c log s to d minus 1. Okay, and let me just give this equation a name because we're going to use this. Okay, so this is equation 5. Okay. Good. So every time I take a step in the walk, the expectation value of my circuit, or more accurately, my multilinear extension of my circuit, does not change too much. Okay. So that means that, if I have something that's not changing so much, then intuitively you want to analyze it step by step and then do some sort of big like sum, right? So a triangle inequality, union bound, something like this, right? And that's exactly what we're going to do. Right? So this basically says that on average, the change in output of C from step I to I plus 1 is bounded by something like 1 over n, right? Well, this is p squared, right? So let me be something like p squared, which is 1 over n, right? So here's your p squared, right? So, roughly something like this, right? Because, well, I should say, I guess p squared over root n more accurately, right? Because I think we set p to 1 over square root of n. No, maybe we don't need that. Okay, take it back. Guess you get that anyway. Okay, but anyway, it's something like 1 over n at least, okay? Good, so let's just apply this on all the steps of the walk, right? So in particular, let's do it this way. So apply to all steps. This is per step, okay? So when you go from I to I plus 1, right? And now let's do it to all steps, okay? So the key thing we wanted to analyze was, what is the expectation of z prime, right? Distributed according to d of the circuit on z prime, right? And we wanted to argue that this is essentially just a constant order term in the Fourier expansion, right? Because that's what we would have gotten on a uniform distribution. So what is the first thing we do? Well, the first thing we do is, remember, we use the fact that, so it's kind of nice because we're going to get to plug in a few of the key IDs we've seen throughout. I want to work with D. D is kind of nasty. And as far as expectation is concerned, though, I can just plug in G prime instead. So that's the first thing I'm going to do. The expectation of Z prime, not according to D, but according to G prime now. That is going to be C of Z. I suppose this should also be, well, let me just put Z to be consistent with the notes. Okay. Oops, what did I just do? Okay. So again, for clarity, this is from Lemma 17 that said the expectations were going to match, basically, of D versus G prime. Okay. And now, what's the next step? The next step is I could write this as the expectation of the circuit of Z. Remember that instead of drawing Z in one shot now I can draw it in terms of taking the baby steps of this random walk, right? Going all the way to the end of the walk, adding up all my samples, and then renormalizing by P, right? So let me just write that all in one step. So you'll notice I'm writing T here in the exponent because this is the full random walk right now. Minus C hat of that thing. Good. And now I'm going to break it up in terms of the random walk. Recursively, okay? Using a triangle inequality, right? Because I can instead write I equals 0 up to t minus 1 now. Of what? Well, now let's just break it up step by step, right? So I have minus e of the value of my circuit on the ith step, after the ith step in the walk, versus the value of my circuit at the I plus first step of the walk. Okay, that's what that is. Okay, and this is just triangle inequality. Okay. And now I can plug in the bound I had before, right? Which is that I know that, I just said this, if I just have one step of the walk, I have a bound on that, right? So let's plug in that bound per step. That's it, okay? So then I have the sum over t, because there are t steps of the walk, right? So I have a sum over t terms, but I'm going to plug in the same term on the right, so I'll just do t times that term. 12 epsilon p squared c log s to the 2d minus 1 all over square root n. And so this is just following from equation 5, right? That was just this thing up here. Okay, and let's see. The the last equation is that this equals to 12 epsilon c log s 2d minus 1, right, over square root n, right? And here, if I'm not mistaken, let's see. So t, we set t to be n, I believe, right? So t was n over here, right? And this thing, I suppose, no, okay. I have to double check why this works, but essentially t scaled like n, right? I think we said p squared scales like 1 over n. So those two should cancel. Oh, good, yeah, exactly right, sorry. So p squared scales like 1 over n, t scales like n, so these two would cancel, and then you get exactly the expression you want without the p there. Okay, so the point is that the damping factor, when we took a step of the walk in deviation, right, scaled like p squared, right? So even though I took n steps, right, and each of them I set p to 1 over square root of n, when you run it through the walk, the deviation per step is 1 over n, so these two will cancel out, okay? And you get exactly the expression you wanted. Good. So that's essentially the end of the proof, basically, that, this is, just to recap, remember this is what the uniform circuit, the expectation for the uniform on uniform samples is, right? And now this is on D samples, if you will. And the point is that, we've just shown that, the difference between these two is very, very small. It scales like essentially 1 over square root of capital N, which is exponentially large in the input size, right? Again, it's important here that D is constant, right? So this the numerator doesn't blow up here. Okay, so therefore the circuit just cannot distinguish between these two distributions, right? The expectations look really, really close, exponentially close. Good. Did I write that? I think we did. So maybe it's good to close the lecture. Let's just put up the main theorem of this last section. This is what we wanted to prove, right? If I have a circuit of bounded depth D, size S, then whether I feed it the uniform distribution or the distribution D, right? On average, the expectation basically is exponentially small, the difference in expectations. So a classical circuit that's bounded depth, and hence also a circuit using a constant number of alternations, like in the polynomial hierarchy, cannot distinguish between these two distributions. Okay, and again, let me be clear, right? Maybe the closing words for this. Okay, so first let me say, okay, the main purpose of this, just to recap, the main purpose of this lecture was to give an oracle separation, right, between BQP and the polynomial hierarchy, right? So there's some oracle-based problem, right, where we kind of picked samples on exponentially large strings according to either the uniform distribution or to this other funny distribution D. We crammed them into an oracle, and we said, if I give this oracle to a quantum machine, it can tell whether I drew the distribution, the samples from D or from U, okay? But a classical bounded depth circuit, even if it's very large size, right, it's not able to distinguish these two distributions, okay, with anything close to 1 over poly probability. In fact, with 1 over exponential is the best it can do. Okay, and there for that we used this Fourier analysis. Okay, and again, so I really want to stress that, this is in the oracle framework, right? I mean, so it's not, it does not in any way imply that BQP is not actually contained in the polynomial time hierarchy, right? I mean, unfortunately, it's not strong enough for that, but in many cases, this is the best one can hope for using state of the art, right? It's very difficult to show unconditional separations, okay? Good, and then, this is also quite a recent result in the last few years. So this is an example of, again, like the last lecture, something that's a lot more modern, a lot more recent, cutting edge. And, in this sense, we will hopefully have covered in the course a broad range of topics going from, introductory to intermediate to, really kind of recent things. Good, that's it for this lecture. I wish you a good week. Stay healthy as always.